Hi everyone. So incidents like these can cause local pollution, which can move the marine environment towards these tipping points that we've been talking about. As a marine engineer, I'm working to prevent these from happening and therefore prevent us moving towards these tipping points. Imagine, if you will, that you are a grain of metal. Not any metal, a metal called nickel, aluminium, bronze. That's made out of copper, iron, aluminium and nickel, all mixed up together. If you were one of my samples, I would cast you into a long rod, I'd then saw you up into sections and I'd weld you. When I weld you, bits of you would get hot, and that could change some of your chemical composition, and that will change some of your mechanical properties, maybe change how strong you are. To be a bit more mean, I then chuck you in the ocean. As we all know, ocean has salt in it. Sodium chloride. Sodium chloride is a great oxidizer. That means your copper starts turning to copper oxide, your aluminium into aluminium oxide. We all know what happens to iron, right? Then things get a bit weird. Things from the deep start coming and brushing up against you. First of all, you get all the macronutrients that attach to you by static electricity. That attracts the bacteria, which attracts the small phytoplankton, which attracts the larger one. And within about 6 months, you are a marine city. The sea squirts are attached to you with glue, the barnacles with cement, and both of these things also change your chemical composition. Also, just their physical presence creates crevice corrosion. All of these things can reduce your strength. But will you fracture? Will you break? This is where my research comes in. So I am looking at how marine life interacts with marine corrosion, or metal corrosion more specifically, and how that affects fatigue life of different metals and different components. Now, when I say fatigue life, I mean how long can we put a component, a piece of metal, into the water, stress it, let go, stress it, let go, stress it, let go. These kind of fatigue stresses are seen all the time in the marine environment. Just think of wave action on a dock. The first thing I do is I get to know my metals really well. So, hi NAB again. This is NAB that has been welded, and you can see really clearly how much that welding heat changes the microstructure of the metal. I'm looking into this using different microscopes, including electron microscopes and other things. I'm also really lucky as an engineer because I still get to go to the seaside quite a lot. I've got 12 metal samples that are literally tied off the end of a dock in Plymouth. They are corroding under the influence of salt and marine life. I've then got 4 sitting in a tank in the university in seawater, but without the influence of marine life. So I can get a really nice handle of exactly what that life is doing. Oh, hello. One of the ways I'm doing this is looking at the change of mass. As you can imagine, if you stick a bit of metal in the water, it's going to start corroding. Those corrosion products are going to be washed away and the mass is going to be reduced. However, there's another signal underneath that, and this is a seasonal signal. In the summer, we have more marine organisms, more marine life that attach to structures, to my metal. This increases the mass, and then they die off in the winter. That's their natural life cycle. It sucks to be a phytoplankton. It's not quite as bad as it looks on this graph. I don't know why it's gone a bit funky. I do apologise, because this doesn't include the buoyancy of the marine animals. But if you can imagine this being a critical component in a ship, or in a wind turbine, in a flood defence in Bangladesh, this could cause massive issues. Another great thing that I get to do, because I just want to tell you about all the cool experiments that I do, is I get to fatigue lots of metal, I get to crack it and I get to break it. And then again, I'm using this microscopy technique to look and see where the cracks initiate, see what type of corrosion is causing those fatal cracks that are going to cause these pollution events that are harming the marine environment. So to kind of wrap up here, my research is really interdisciplinary, and that's why I love it. I'm a bit of a hybrid myself. I cover engineering, chemistry, marine biology, and that's just what I've been talking about to you guys in the last 4 minutes. What I'm now working together with various engineering institutes is actually to try and increase the amount of exposure that marine engineers get to marine scientists so that we can understand the chemistry and the biology a little bit more. In this way, we should be able to work together to increase the environmental sustainability of our marine structures, and also make marine structures that are going to increase the marine biodiversity by purposefully becoming hosts for marine ecosystems. Now, all of this, I hope, will move us away from some of these global tipping points. And I think that's a reason to be hopeful. Thank you.